Have you ever looked up at a skyscraper during a windstorm and wondered why it doesn't just snap in half? Buildings like the Burj Khalifa stand over 800 meters tall. That's nearly half a mile straight up. And at those heights, wind speeds can exceed 150 miles per hour. That's hurricane force wind, constantly battering a structure weighing hundreds of thousands of tons. By intuition, something that tall and slender should topple, but it doesn't. Today, we're breaking down how skyscrapers survive high winds. And I promise, after this video, you'll never look at a tall building the same way again. To understand the scale of the challenge, consider the Burj Khalifa in Dubai. It stands 828 meters tall, that's over half a mile straight up, and weighs approximately 500,000 metric tons. That's roughly the weight of 100,000 elephants, all stacked vertically into the sky. At ground level, wind might be calm, but at 800 meters, wind speeds regularly exceed 150 miles per hour. That's Category 4 hurricane force, sustained hour after hour. And the force wind exerts on a building increases dramatically with height. At 400 meters, wind pressure can be 4 times greater than at ground level. For a structure this tall, lateral wind loads can exceed the building's own weight. By common sense, something that slender should buckle or topple, but physics and engineering say otherwise. Humans didn't always know how to build tall. In the 19th century, masonry walls limited building height. Thick stone could only support so much weight before crushing itself. The home insurance building in Chicago, completed in 1885, changed that. It was the first to use a steel skeleton frame, allowing walls to be curtains rather than load-bearing structures. Height jumped from 10 stories to 16, then came the Woolworth Building in 1913, reaching 241 meters using steel and masonry. But engineers quickly realized that as buildings grew taller, wind became the dominant design challenge, not gravity. The weight of the structure could be managed through stronger materials, but lateral forces required entirely new thinking. In 1931, the Empire State Building rose to 381 meters. Its designers used a steel frame with riveted connections, and the building's mass provided stability against wind. But it swayed noticeably during storms. Occupants on upper floors could feel the motion. After World War II, advances in materials and analysis methods accelerated. In 1973, the Willis Tower in Chicago introduced the bundled tube structure reaching 442 meters. This was a breakthrough. Instead of a single core, 9 tubes were clustered together, each reinforcing the others. The design distributed wind loads more efficiently and reduced sway. By the 1990s, engineers were using computer simulations and wind tunnel testing to model airflow around buildings. In 2010, the Burj Khalifa proved that even an 828-meter tower could withstand extreme wind through precise structural engineering and aerodynamic shaping. But despite all the innovation, the core challenge never changed: managing lateral forces. So how does a skyscraper actually resist wind? The answer lies in 3 integrated systems: the structural frame, load distribution, and material properties. Every tall building must channel wind forces from the exterior surfaces down to the foundation without exceeding the strength limits of steel or concrete. Think of it like a vertical cantilever beam, fixed at the base, free at the top, resisting bending along its entire height. When wind hits one face of the building, the entire structure must respond as a unified system. You've probably heard that skyscrapers are just solid masses of concrete and steel. That explanation is incomplete. The primary structural approach is the tube structure. In this design, the building's perimeter consists of closely spaced steel columns connected by horizontal beams called spandrels. Together, they form a rigid hollow tube. When wind strikes the building, the tube distributes the load around the entire perimeter. This does three main things. 1. The windward columns experience compression. 2. The leeward columns experience tension. 3. The side columns handle shear forces. The entire exterior acts as a structural element, not just the core. The John Hancock Center in Chicago, completed in 1969, used exterior diagonal bracing, visible X patterns on the facade. This created a braced tube, dramatically increasing stiffness against lateral loads while reducing the amount of steel required. Another approach is the shear wall system. Reinforced concrete walls, typically arranged around elevator and stairwell cores, resist lateral forces through shear strength. When wind pushes the building sideways, these walls act like vertical plates anchored to the foundation. The load travels down the wall and into the ground. Shear walls are highly effective but require careful placement. They must be continuous from top to bottom and symmetrically distributed to avoid torsional twisting. Many modern skyscrapers combine both systems. A reinforced concrete core with shear walls, surrounded by a steel perimeter tube. This hybrid approach maximizes both stiffness and material efficiency. The load path is critical. Wind strikes the building's facade, creating pressure on the windward side and suction on the leeward side. These pressures transfer through the cladding into the structural frame, first to spandrel beams, then to columns, then to floor slabs, and finally to the core or foundation. At every connection, forces must be transmitted without failure. Engineers design each joint, bolt, and weld to handle calculated maximum loads multiplied by safety factors. There's no magic involved, just forces and balance. But structure alone isn't enough. That's only part of the story. A skyscraper doesn't just resist wind, it responds to it dynamically. Buildings are not rigid objects. They behave like vertical pendulums, swaying back and forth when wind gusts hit them. The taller the building, the longer the natural period of oscillation. For a 400-meter tower, the sway period might be 6 to 8 seconds. During a storm, the top of the building can move horizontally by 30 to 50 centimeters or more. That motion is usually invisible from the ground, but occupants on upper floors can feel it, and that creates a problem. Even if the structure is perfectly safe, excessive acceleration causes discomfort, nausea, and fear. Engineers must limit not just displacement, but the rate of acceleration. Building codes typically restrict peak acceleration to around 0.015 to 0.025 drg, enough that most people won't feel sick. This is where damping systems come into play. Damping dissipates energy, reducing the amplitude of sway. One of the most effective devices is the tuned mass damper. The Taipei 101 Tower in Taiwan houses a 660-ton steel pendulum suspended between the 87th and 92nd floors. When the building begins to sway in one direction, the pendulum swings in the opposite direction, creating a counteracting force. The damper is tuned to the building's natural frequency, so it resonates out of phase with the structure. This drastically reduces peak sway by up to 40%. The mass doesn't stop the building from moving, but it smooths the motion and prevents large oscillations from building up over time. Other skyscrapers use different damping strategies. Outrigger trusses connect the building's central core to the perimeter columns, creating a stiffer system that resists bending. Viscous dampers, cylinders filled with thick fluid, are installed at key structural joints. As the building flexes, pistons move through the fluid, dissipating energy as heat. Some buildings incorporate friction dampers, where steel plates slide against each other under load, converting kinetic energy into friction. The choice of damping system depends on building height, structural type, wind climate, and cost. But the principle is always the same. Absorb and dissipate energy before it accumulates into dangerous or uncomfortable motion. Now let's look at the same challenge from another angle: aerodynamics. Wind doesn't just push, it also creates complex turbulence and vortex shedding. When wind flows around a sharp-edged rectangular building, it separates at the corners, forming alternating vortices that peel off from each side. These vortices create oscillating lateral forces perpendicular to the wind direction. If the frequency of vortex shedding matches the building's natural frequency, resonance occurs, amplifying sway dramatically. This phenomenon caused the original Tacoma Narrows Bridge to collapse in 1940, and engineers work hard to avoid it in skyscrapers. To reduce vortex shedding and overall drag, architects shape buildings aerodynamically. This does three main things. 1. Tapering the building as it rises reduces the cross-sectional area at higher elevations, where wind speeds are greatest. 2. Setbacks. Stepped reductions in floor area. Break up the wind flow and prevent continuous vortex formation. 3. Rounded or chamfered corners smooth airflow, reducing turbulence. The Burj Khalifa uses a Y-shaped floor plan with a stepped, spiraling profile that confuses the wind, preventing organized vortex patterns from forming. Wind tunnel testing during the design phase revealed that this shaping reduced lateral loads by approximately 25% compared to a simple rectangular tower of the same height. Every curve, every setback, every detail of the facade is informed by aerodynamic analysis. So how do engineers actually design for wind? The process begins with wind data, historical records of wind speeds and directions at the building site. Engineers determine the design wind speed, typically based on a 50-year or 100-year return period storm. Then they build a scale model of the building and surrounding structures and place it in a boundary layer wind tunnel. Fans generate wind profiles that simulate real atmospheric conditions, and sensors measure pressure on every surface. The data reveals exactly how wind loads distribute across the building's height and where peak forces occur. Modern projects also use computational fluid dynamics, running simulations that model airflow with millions of data points. The results guide structural design, where to add bracing, how thick to make concrete walls, what damping devices to install. Engineers then apply safety factors, typically 1.5 to 2.0 times the calculated maximum loads, to ensure the structure can handle unexpected conditions. Every beam, column, connection, and damper is designed with margin. Building codes like ASCE 7 in the United States and Eurocode 1 in Europe provide standardized methods for calculating wind loads. But for super tall buildings, site-specific testing is always required. No two sites have identical wind conditions, and no two buildings respond the same way. Inside the Burj Khalifa, during a strong wind event, occupants might notice the building swaying gently, perhaps a slight sense of motion, like being on a large ship. But that motion is controlled, predictable, and well within safe limits. The structure is not in distress. The steel and concrete are experiencing stress and strain, but nowhere near their failure points. The dampers are doing their job, absorbing energy. The aerodynamic shape is deflecting wind efficiently. Everything is working as designed. That's how hundreds of thousands of tons stay upright in 150 miles per hour winds. Every time you see a skyscraper rising above a city skyline, it feels like it's defying nature. But it's not breaking the laws of physics, it's using them. Structural systems, damping devices, aerodynamic shaping, everything exists in precise balance. To me, that's the real beauty of structural engineering. Not magic, but exact calculations and a deep respect for the laws of nature. And now I'm curious. Have you ever wondered how engineers design skyscrapers to survive earthquakes?